All right, we've been working with exponential expressions and following the exponent rules to simplify those. So now we're going to take that one step further and look at actual exponential functions, and we're going to be graphing these and evaluating them for specific x values. Now, the other equations that we've dealt with, we've had an initial amount, and then we've had a rate of change. We've used things like slope-intercept form, y equals mx plus b. And so we've had linear equations. Now this one, the rules are a little bit different. The independent variable, which is your x, usually y equals mx plus b, our independent variable is typically multiplied by our slope or our rate of change. For this one, our independent variable is actually going to be our exponent. Now this is a look at what exponential function is, the definition. The exponential function is written in the form y equals a times bx. Now think back to your exponent rules. We can't combine the a and the b here. They're not like bases. If they were, we could add the exponents, but they are not like bases, so we have to leave them separated like this form. Now a is not going to be equal to 0, so it can be pretty much anything else except 0. And then b has to be greater than 0, but not equal to 1. So this is kind of confusing for some people because 1 is obviously greater than 0. What this means is that we can have everything between 0 and 1, like 1/2, 1/3, those sorts of numbers. And we can have everything larger than 1. So we have to start at 0, but we cannot include 1 in that number set for b. And then x can be any real number. Now these are 4 examples here of exponential functions and their graphs. Y equals 2 to the x power and y equals negative 2 to the x power. So you can see how those two graphs compare to each other. And then this is y equals 1/2 to the x and y equals negative 1/2 to the x power. So you can see how those compare. Now there's a few things that you need to point out and think about when you're looking at these two graphs, or these 4 graphs. All of them actually have a y-intercept. If I ask you what the y-intercept is, you would be able to tell me where it is, where it crosses the y-axis. But if I ask you where the x-intercept is, some of you all would start trying to make some guesses, but it is very difficult, especially looking at these two graphs. Even though the red and the blue in both of these examples look like they are touching the x-axis and actually running along the x-axis, they aren't. For exponential functions, you will not have an x-intercept. It does not ever cross the x-axis. It's going to continue to get closer and closer to the x-axis, and your fractions are going to get smaller and smaller, but you are never going to actually reach the x-axis, so you will not have an x-intercept. If you think about cutting a piece of paper in half, we can continue to cut the paper in half over and over and over again, and even though we're going to reach a point where we can physically not cut it in half, you're still going to have a half a sheet of paper in your hand. So you'll never actually eliminate the paper altogether. So that's kind of like what exponential function is as far as x-intercept. It's going to continue to get close to the x-axis, but never actually touch it or cross it. So let's look at a couple of examples, a table and an equation. This table, we want to determine if it represents a linear or an exponential function. Now let's think back to linear. Linear equations, we were increasing at a constant rate, adding 1 every time or adding 3 every time. It was staying constant every time with our x's and our y's. With exponential functions, those are going to be a little bit different because we're going to be growing or decreasing very quickly, exponentially. So it's going to be multiplying by a number and staying constant with that multiplication. So let's look at part of the explanation. Let's just think about this right here first. How can you identify a constant ratio between y values? Now think about a ratio, a over b. We're looking for that ratio. When you multiply each y value by the same constant, so multiplying by the same number every time, and you get the next y value, then that means you have a constant ratio between values. So look at our example here. If I take negative 1 and multiply by 3, I get negative 3. If I take negative 3 and multiply it by 3, I get negative 9. So I'm multiplying by the same constant every time, which is 3, and getting the next y value. So that's the ratio between each y value. Now take a look at your x values, the difference. And the difference in 1 and 0 is 1. The difference in 2 and 1 is 1. So I'm increasing by adding 1 every single time. So my common difference for my x values is 1. So I have a common difference for my x's and a common ratio for my y's. Okay, two different things here that you've got to focus on when determining linear or exponential. So because this table has a common difference in your x values and a common ratio for your y values, this table represents an exponential function. If you are multiplying by 3, then multiplying by 3, and then all of a sudden it changes and starts multiplying by 5, that is not a common ratio. So that would not be an exponential function. So be very careful with that. But also be very careful to make sure that your x's are increasing the same, to make sure that your y's are increasing the same. If your x's have a big jump and they've skipped several numbers in between, you've got to be very careful with the numbers that have been skipped with the y. So always double check your x's in your table. All right, so now let's look at an equation. We want to know y equals 3x. Is that linear or exponential? Well, let's take a look again at our exponential form. Y equals a times b to the x power. Look at this form and then look at your question. Do they match? Where's your x located? In exponential function, it should be the exponent. But in our equation, it is actually just being multiplied by 3. 3 would be considered our slope. This is actually in y equals mx plus b, where b is 0, form. So 3 is our slope, x is our independent variable, and it is not the exponent. So that means that this is a linear function. The independent variable is not an exponent, so it's not exponential. Be very careful. If the x had been up here as the exponent, then this would be exponential. All right, so let's take a look at an example. Here's your table. Look to see, are your x's increasing at a common difference? Do they have a common difference? And do your y's have a common ratio? Now here's your answer choices. Notice you've got 2 no's and 2 yeses. So what you have to be very careful of is the explanation. Make sure the explanation matches y, yes or no. All right, pause the video and take a minute to do that. Your correct answer is B. Okay, the y values are not multiplied by a constant amount. Your x's are increasing correctly, but your y values are not being multiplied by a constant amount. All right, let's take a look at another example.
In this problem, you will evaluate the exponential function. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. The function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? Step 1. Convert 56 days to weeks.
This is extremely important, and you need to pay attention to this when solving any type of word problem. Look to see what the units are for your independent variable x, and then you need to look at what they've given you. And since our units do not match, one's in weeks and what we've been given is days, you have to convert that. So always be very careful with word problems.
Write a proportion relating days to weeks. How do you write a proportion relating days to weeks?
We've written several proportions. Think about setting up ratios and then setting the two ratios equal to each other to set up your proportion.
Use the fact that there are 7 days in 1 week. So the ratio 56 days to x weeks equals the ratio 7 days to 1 week. Now write the proportion without units. Use the cross products property. Divide each side of the equation by 7. So x equals 8. 56 days equals 8 weeks.
Now you may be able to convert that without setting up the proportion, but always be very careful with your units.
Step 2. Evaluate the function for x equals 8. Write the function. Why is the function 30 times 2 to the x power instead of 2 times 30 to the x power.
Think back to what the question and what the word problem has told you.
In an exponential function, y equals a times b to the x power. A is the starting value, and b is the rate of change. In this case, the starting value is 30. Since the population is doubling, the rate of change is 2. Substitute 8 for x. Simplify the power. Now simplify. After 56 days, there will be 7,680 beetles. Grade your answer.
Okay, I'm not worried that you can grid your answer, but 30 is how many flower beetles you started out with in this warehouse, and they're doubling every week. So that means X is your weeks. Every week you're doubling the amount. Now it seems like you would multiply 2 times X, but they're growing exponentially. They're growing very quickly. Every flower beetle is doubling. So the population itself is doubling. So it is exponential. So 30 is your starting value. 2 is your rate of change, and then you substitute in your weeks.
Now it's your turn.
All right, so quickly pause the video. Here's your answer choices, and go through and solve this just like the last example. They've already set up the function for you. 20 is your starting value, 3 is your rate of change. But what you got to be very careful of is X represents half-year periods, half years. So if you think about in 1 year, there's actually 2 half years. So they give you 3 years as your unit, so make sure that you convert that correctly and determine how many rabbits there are. So pause the video and do that quickly. All right, your correct answer is D, and this is how you would make sure you've got the correct unit or the correct amount for your X. Substitute in and simplify. All right, last example is graphing.
In this problem, you will graph an exponential function. What is the graph of the function y equals 3 times 2 to the x power? What is the domain and range of the function?
Domain are your x's, range is your y.
Any value substituted for x results in a positive y value. The domain is all real numbers. The range is all positive real numbers.
Basically, you can substitute any number you want to in place of x, and you're going to get its y value that it's matched up with. So you can have pretty much any y value as a result.
Make a table of x and y values. Start with x equals negative 2.
Now notice he picked negative 2 and he's just plugging it in for x and then simplifying.
When x equals negative 2, y equals 3/4.
This middle column is just showing
Next,
your work.
Let x equal negative 1.
Now you can pick any x values you want. These are just the ones that he's using for this example.
When x equals negative 1, y equals 1 and 1/2. Next, let x equal 0.
All right, so here's all the values. Make sure you get those copied down.
Graph the function.
I just went ahead and clicked on because I wanted you to see 0, 1, and 2. Go ahead and fill those in, and then now he's going to graph the function. Plot all of your points
in the table. Then, connect the points with a smooth curve.
Notice that you have a y-intercept but no x-intercept. It looks like it's going to reach x, but it's not. We will get more practice with graphing in class.